Hello students, welcome you all to the session of Solutions for GATE 2022 Mechanical Engineering Branch Set 1 Strength of Materials. First question. An L-shaped elastic member ABC with a slender arms AB and BC of uniform cross section is clamped at end A, that is at this point, and connected to pin at end C. The pin remains in continuous contact with and is constrained to move in smooth horizontal slot. The section modulus of the member is same for both the arms. The end C is subjected to horizontal force P and all deflections are in plane of figure given the length AB is 4A. The length BC is the magnitude and the direction of normal force on the pin from the slot respectively are option A 3p by 4 and upwards, option B 3p by 8 and upwards, C p by 4 and downwards, D 3p by 8 and downwards. This is the question given to you. Now when I see this diagram, the force P is acting in this direction. Let us consider x direction and y direction in this way. This is y and x. Now point C will move in x direction due to applied force, right? And its deflection will be 0. Deflection will be equal to 0 in y direction. In y direction. Assuming slot provides reaction, that is the slot at A will be giving the reaction in y direction, the free body diagram will be like this is B, this is A, this is C. The reaction will be R and the force applied is P, right? This length is A, this is 4A. Deflection at C in y direction is 0. That will be a deflection at B in y direction. Same way, if this is the condition, this is 4A, at point B you have some reaction and also the moment force will be in the x direction. This will be the moment. So delta B, deflection at B in y direction will be PA into distance is 4A whole square by 2EI plus, due to R it is R into 4A whole cube by 3EI, which will be equal to 0. I am considering it is a cantilever beam. The reaction due to some force P at a distance A and reaction R with a distance of 4A. So obviously from here find the value of R. Find the value of R because delta B in y direction, this term becomes 0, right? So if we find the value of R from here, you should get around minus 3p by 8. See, upward direction I took as positive, so minus sign resembles acting in the downward direction. Negative sign means reaction in the downward direction. So the answer R is 3p by 8 in the downward direction. Downward direction. So option D will be the right answer for the given question here. 3p by 8 in the downward direction will be appropriate right answer for the given question. Moving to the next question. A thin-walled cylindrical pressure vessel has a mean thickness of T, nominal radius of R. The Poisson's ratio of the wall material is 1 by 3, which is mu. When it is subjected to some internal pressure, its nominal parameter in the cylindrical portion is increased by 0.1%, corresponding to the wall thickness of T bar. The corresponding change in wall thickness of the cylinder portion, that is 100 times T bar minus T by T, is dash percent. Round off the decimal place. Basically, the solution is hoop stress can be given as, this is a question from thin cylinder, right? PD by 2TE into 2 minus mu strain. Right? How much is the nominal parameter in the cylinder portion is increased by 0.1 by 100 because 0.1 percentage is given. Change in thickness delta T will be equal to epsilon R into T. This formula is directly minus mu hoop stress plus longitudinal stress by Young's modulus into T. From here, delta T will be is equal to minus mu by E 3 by 4 PD by T into T. Right? 3 by 4 PD by T into E. This can be written as delta T is equal to minus mu into T 3 by 4 PD by TE. Simple. I am taking E outside and cancelling of the T value. That will be. So, here from one equation I got around hoop strain. This is your delta T value. Now, from equation 1 and 2, what happens? Delta T is equal to, substitute minus mu T into 3 by 4, or we can write it as minus 3 into the percentage of cylindrical radius 0.1 by 100 into 1 by 2 minus mu. From here, delta T by T I want to take minus 0.3 by 100 into mu by 2 minus mu. On solving it, mu is 1 by 3 given, minus 0.3 into 1 by 3 by 100 into 2 minus 1 by 3. Solve this. Minus 0.3 into 1 by 3 by 100 into 2 minus 1 by 3. It is 6 into 10 power minus 4. Delta T by T in percentage into 100 will give you around minus 0.06%. Minus 0.06%. This is the answer for the given question. He asked question 100 into T bar minus T by T is dash percent minus 0.06. This is the condition. So this will be the appropriate right answer for the given question. Moving to the next question. Assuming material considered in each statement is homogeneous, isotropic, linear, elastic, and the deformations are in the elastic range, which one or more of the following is or are true? If a long solid steel rod is subjected to tensile load, the volume increases. If beam of a has zero shear force, then the corresponding portion of the elastic curve of the beam is always straight. C. Maximum shear stress theory is suitable for failure analysis of brittle material. D. Body subjected to hydrostatic pressure has no shear. Here the conditions is asking you. First, I'll talk about a body subjected to hydrostatic pressure has no shear force. Obviously, this point is from fluid mechanics. Whenever we consider a body, that is hydrostatic pressure force acting on the body, shear stress tau will be is equal to 0. This is a basic fundamental. So option D first of all will be one of the right answer. Coming to C. maximum shear stress theory is suitable for analysis of brittle materials? No. No. Basically, what happens is shear stress on all planes will be equal to 0. First thing, the planes are, all the planes will have principal planes. That is, if I take the explanation in this way, cubic element, this is the stress which is acting. Now, under hydrostatic conditions, ductile materials will behave like brittle condition, right? Hydrostatic or spherical stress conditions, which I am teaching you here. And axial loading applications of tensile stress will lead to volume increase, and the application of compressive stress will lead to volume decrease. And that way, biaxial and triaxial conditions, biaxial or triaxial conditions will be like sigma x plus sigma y plus sigma z will always be greater than 0. And the most suitable theory of failure for brittle materials, what happens? Maximum principal stress theory, not principal shear stress theory, it is maximum principal stress theory. And most suitable factor of, theories of failure for ductile material will be distortion theory, and conservation theory of failure will be maximum shear stress theory. So obviously under axial loading condition, all theories of failure will give similar results, Now from this conclusion, I can clearly say that a long steel rod subjected to tensile load, volume will be increasing. Yes, this is also I can give the answer as. But C is not at all correct. The portion of beam has zero shear force. The corresponding portion of the elastic curve for the beam is always straight. No. So obviously A and D, right? A and D will be the right answer for the given question. It is a multi-select question like thing. More than one option you are going to get. Options are a body subjected to hydrostatic pressure has no shear stress, which is D, and if a long solid steel rod is subjected to tensile load, its volume is going to increase. Option A and D will be the right answer for the given question. Moving to the next question. A uniform light slender beam AB of section modulus EI is pinned by frictionless joint A to the ground and supported by light in extensible cable of CB. Hang to the weight of W as shown. Supported by light in extensible cable CB to have a weight W as shown. The maximum value of W to avoid buckling of the beam is obtained by beta pi square EI, and pi is the ratio of circumference to diameter of the circle. The value of beta is A 0.0713 meter per minus 2, B 0.092 meter per minus 2, C 0.1417 meter per minus 2, D 0.1261 meter per minus 2. Now, I'll draw free body diagrams for each and every link. First I am taking with A. Let this be A, which is pinned. This is B. There will be a tension in this rope T. Weight force will be acting downward. Angle made is 30 degrees. So obviously when you resolve the forces, this will be T cos 30. This is T sin 30 degrees. So from here, if I take summation of Fy equal to 0, vertical forces, I will be getting T sin 30 is equal to W. That is T by 2 is equal to W. T is equal to 2 times W. Let this be equation number 1. Now I'll take column AB pinned at the bottom ends. That is, this is the slender rod like thing, right? This is A, this is B. There is some force which is acting. This will be 2W cos 30. The length is 2.5 meter. So obviously this will be 2 into root 3 by 2 W because cos 30 root 3 W. Now we know that the crippling load is pi square EL by L square, that is effective length. Length is how much? 2.5 meter. Crippling load is how much? Root 3 W is equal to pi square EI by 2.5 square. That is W is equal to pi square EI by root 3 into 2.5 square. From here, if you modify it, simplify it, 0.0924 pi square EI. Now, what is given to you? Beta pi square EI. What will be the value here? Compare this with beta pi square EI. Value of beta will be 0.0924. That will be option B. 0.0924. Beta is 0.0924 meter per minus 2. Got it? This will be the answer for the given question. These are the questions from Strength of Material of GATE 2022 set 1. Hope you people have understood. Thank you, students.